I gave an AI agent 100 synthetic vulnerability findings and asked it to choose the 10 that deserved analyst attention first. The result was not a clean success. It found the 2 cases I cared about most. It ignored an obvious critical severity trap, but only 3 of its top 10 matched the separate analyst rubric, and on some findings it confidently described evidence that was not in the data. That failure is more useful than another perfect demo because it shows exactly where an AI agent can help vulnerability management and where it should never make the final decision alone. I generated 100 fictional findings across production, staging, internal, and lab systems. Each finding included CVSS, severity, internet exposure, known exploitation, public exploit, availability, business criticality, sensitive data impact, patch availability, confidence, age, and compensating controls. No real company data was used, and nothing was scanned. Then I created a separate analyst rubric that rewarded active exploitation exposure, production importance, and business impact while reducing priority for low confidence findings, lab systems, and documented controls. The agent did not receive the final analyst ranking. It received the evidence and had to return its own top 10 with reasons. 2 findings were designed to test whether the agent understood context instead of sorting by severity. Vulnerability 042 had a CVSS score of only 6.8, but it affected an internet-facing production authentication system, appeared in the known exploited set, had a public exploit, and involved sensitive data. The analyst rubric ranked it first. The agent ranked it second. Vulnerability 007 had a CVSS score of 9.8, but it was a low confidence finding on an isolated lab system with a compensating control. A severity only list placed it near the top. The agent correctly left it out. The agent's first 2 choices were meaningful. It ranked vulnerability 073 first because it was internet-facing, production, high, criticality, connected to sensitive data, and had a public exploit. It ranked the known exploited medium severity case second. It also included vulnerability 037, a critical internet-facing production finding with high asset importance and no compensating control. Those 3 findings also appeared in the analyst top 10. So the agent was not randomly guessing. It recognized several important relationships that CVSS alone would miss. But 3 correct choices out of 10 is not enough for an unsupervised remediation queue. The final precision score was 30%. 7 findings expected by the analyst rubric were missing from the agent's top 10. Several were older exposed production findings with strong business context. The agent also elevated findings that had documented controls, weaker environments, or lower analyst scores. One example was vulnerability 088. It had a CVSS score of 9.9 and affected production, but it was not internet-facing, was not known to be exploited, and had a compensating control. The agent still placed it 9th. That is a familiar failure pattern. The model noticed the dramatic severity and sensitive data labels, but did not consistently apply the mitigation evidence. The ranking error was not the worst part. For vulnerability 068, the agent claimed public exploit activity, sensitive data exposure, high asset criticality, and production use. The actual record described a lab finding with no public exploit, no sensitive data, and no production exposure. For vulnerability 086, the explanation also mentioned sensitive data and a public exploit even though both fields were false. The agent produced fluent reasons, but some reasons were not grounded in the input. If those explanations were copied into a ticket or executive report, the workflow would turn model confidence into false evidence. That is why traceability matters as much as the ranking itself. I would not solve this by asking the model to try harder. The safer design separates calculation from explanation. First, code normalizes the scanner data and validates required fields. Then deterministic rules calculate priority from known exploitation, exposure, asset context, confidence, age, and controls. After that, the AI agent can explain the already ranked candidates, group related findings, draft remediation notes, and identify missing context. Every explanation should cite the exact fields that support it. A validator should reject any sentence that introduces evidence not present in the source record. Finally, a vulnerability analyst reviews the queue before tickets, exceptions, or production changes move forward. That architecture uses the model for language and investigation while keeping risk scoring evidence bound and reviewable. This experiment does not prove that AI cannot prioritize vulnerabilities. It proves that a single prompt, a large input list, and a confident answer are not a production control. The agent found valuable signals. It beat a simple severity sort on the 2 design traps, but it missed 7 benchmark priorities and invented context in its explanations. The useful version is not an autonomous risk decision maker. It is a supervised triage assistant with deterministic scoring, source-grounded explanations, validation, and human approval. If you are finding this content useful, please subscribe, like, and comment. Thanks for watching. I will keep testing these systems honestly, including the parts that fail, and I will see you in the next one.